Okay, so we'll get started. So last time we were talking about kinetic energy. And so we were nearly finished. And or at least finished with the initial discussion. So we were talking about the kinetic energy of an interconnected mechanical system. Okay, so remember the idea was we had one of these things, and it had a configuration manifold Q. Okay, and we defined the kinetic energy of that thing, and we did this by first defining the kinetic energy for a rigid body undergoing a prescribed motion. Then we took an interconnected mechanical system, put it in motion. All right, and therefore each of the individual bodies was in motion, and we derived the kinetic energy for a single body and therefore for an interconnected mechanical system. And then what we did was we interpreted that kinetic energy along a motion to give us a function on the tangent bundle of the configuration manifold. Okay. So that's kind of where we were last time. And then at the end, what we looked at we saw that if we fix a configuration Q, okay, so if we're fixed Q in Q, the function VQ, okay, so velocities at Q, so VQ is in the tangent space at Q, maps to kinetic energy at VQ, okay, is, it had two properties. So first, it was quadratic. Okay, so it's a function on a vector space, all right, so it makes sense to say that it's quadratic, and non-negative. Okay, now the point of that is to notice that a quadratic non-negative function, in fact, what we're going to see is that it's even more than non-negative. It's in fact going to be positive except at zero. Okay, in which case, because it's quadratic, it's obviously zero. All right, and so the idea is that a function like that comes to us in a form with which we are familiar. Okay, so if you think about it for a second, how do quadratic functions on vector spaces arise? Okay, and you know, what does it mean to be a quadratic function even on a vector space? Okay, so let's look at a simple example to start out with. So maybe let me do this. Quadratic functions on vector spaces. Okay, just to think a little bit carefully about what that means. So first, let's look at the vector space that we're familiar with. Okay, so what would a quadratic function mean? So a quadratic function on Rn is of the form x. Okay, so x is a vector in Rn. So let me maybe write it as V. Okay, so it's a quadratic function. So what does that mean? So that means that V appears, you know, quadratically. And what should that look like? So that should look like something like this. So if V is a vector that has components v1 up to vn, okay? A quadratic function is, a quadratic function. So v appears, the components of v in this case appear quadratically. So what's the observation that we make here? Well, the observation that we make is that we have these coefficients b, okay? And what is b? Okay, so if you take those, well, the b's are just numbers in that formula, but certainly there's some properties that you should think of which look familiar to you about those b's, and that is that the b's should be thought of as being the components of a bilinear map. Okay, so think of, whoops, of BJK. Okay, and so this bilinear map, I'm obviously going to call B. All right. And so this now turns this formula into something involving something that we're familiar with, namely a bilinear mapping. All right. Now, let's think about that a little bit harder. So I claim that without loss of generality, you can assume that B is symmetric. So without loss of generality, we can assume that B is symmetric. So in other words, B is in this space of symmetric bilinear mappings, which we denoted like so. Okay, now why is that? Well, let's look at this formula that defines this quadratic function. Okay, certainly, so we're summing here over J and K. Certainly, in this part of the expression, the Vj, Vk part, that's certainly symmetric in J and K, right? So Vj, Vk is the same thing as Vk, Vj. Those are just scalars that I'm multiplying together, okay? And so if B wasn't symmetric, okay, then what you would do, so we're going to see this argument shortly, and I'm going to go through it more carefully then, but let me just sort of do it quickly here, kind of off to the side. So if B was not symmetric, I would write Bjk as a symmetric part plus a skew symmetric part. Okay. All right. So this one is clearly symmetric in J and K, and this one is clearly skew symmetric in J and K. When you swap J and K, you change the sign of that term. All right. Now, if you look at what happens when you put this part into an expression like this, okay, the symmetry of these guys and the skew symmetry here will cause that part of the sum to be 0. And so, the only thing that will remain in the sum is the symmetric part. Okay, so like I said, I'm gonna, in a slightly different context, I'm gonna argue that a little bit more carefully, but for now, we can just make that observation. Okay. All right, so the point is, indeed, for an arbitrary vector space, V, okay, a quadratic function is F, and I'm going to call it F sub B because it's going to depend on a B. It's going to be a function on V. Okay, so it's F sub B of V is going to be B of VV, okay? Because if you think about in this formula, B is being the components of a bilinear mapping. This is just B acting on V comma V. Okay, so that's how you define a quadratic function in general. Okay, so a quadratic function has assigned to it a bilinear mapping B, and moreover, that bilinear mapping is unique if we also require it to be symmetric. Okay, and moreover, B is uniquely determined by this formula. If we require B to be symmetric. Okay, so the point is, when I say quadratic function, the point is that's really synonymous with symmetric bilinear mappings. Okay, and then the point is we've seen those before. We spent some time talking about those. Okay, all right, so let's apply these observations then about quadratic functions on vector spaces. Let's apply those to the kinetic energy, which we've observed is quadratic and non-negative, okay? And non-negative means positive semi-definite, okay? So thus, K, let me put it this way. So thus, for each Q in Q, there exists okay, because on the tangent space at Q, the kinetic energy is a quadratic non-negative function. So that means there exists a symmetric, positive semi-definite bilinear mapping on the tangent space. Okay, so there exists a positive, so let me put symmetric, positive semi-definite, okay, bilinear mapping. And so I have a special symbol that I'm going to use for that. That's going to be G of Q. And so this is going to be symmetric and bilinear on the tangent space at Q. Okay. All right, so that's geometrically how the kinetic energy comes up. What it's not the kinetic energy function that I really care about. Okay, I don't really care about that. What I actually care about is this. Okay, so the same thing here. If I have a quadratic function f sub b, what I'm saying is that I'm going to concentrate on b, not f sub b. Okay. All right, so that thing has a name. So we call G, okay? So G is going to be a mapping which assigns to every point Q a symmetric, positive semi-definite bilinear mapping on the tangent space at Q. This is called the kinetic energy metric. Okay, so in practice, okay, so I've written, all we know from what we've said so far is that G is positive semi-definite. In fact, just as a natural byproduct of doing this in practice, G will be actually positive definite, not just positive semi-definite. Yeah, definite. Okay. All right. So this, it turns out, is a rather important thing in the framework of modeling that we're going to talk about. Not very clear exactly right now why this is so important. Okay, but it is. All right. So we're gonna do two things. First, we're going to just sort of see the notation for representing G. Okay. To write G in a chart U phi with coordinates Q1 up to Qn. All right, so basically when I'm doing geometry, I use X's as coordinates, and when I'm doing mechanics, like I'm doing here, I use Q's. Okay. Right? Although G is a purely mathematical object, right? It's you have a manifold, Q in this case, and at every point in the manifold, you assign a positive definite bilinear mapping on the tangent space at that point. And it's a purely mathematical construct. And that mathematical construct is what's called a Riemannian metric. Okay, so that's making reference to a whole big field of differential geometry called Riemannian geometry. And so the Riemann there is Riemann of the Riemann sphere and of the Riemann integral. Okay, so Riemann. And so there's a purely mathematical aspect to this, but we're thinking now about the mechanical element of this. So I'm going to write it as coordinates as Q. Okay. Okay. We have. Okay, so now what we need to do is we need to kind of harken back to our discussions of linear algebra. Okay, and we talked about bilinear mappings there, and we talked about representing bilinear mappings in a basis. Okay, so that's a while ago now, but that's okay. We all have super fine memories, and we remember that the way you write, and so down here I'm going to sort of just sort of temporarily do the linear algebra part of this. And so if I have a vector space V, okay, with a basis E1 up to En, okay, and then we have E super 1 up to E super N, the dual basis. Okay, and B, a bilinear mapping on V. Okay, then we write B as B, J, K, E, J, tensor, E, K, right? That was the linear algebra version of the formula that I'm going to write down now in a geometric setting, okay? And so for us, the vector space V is going to be, of course, the tangent space, okay? The basis, all right, so again, it's been a while since we talked about this, so maybe let me do another kind of aside here. So for us now, V is T, Q, Q. EJ is the coordinate basis, d by d QJ. And then the dual basis, remember we had notation for the dual basis, it was like that, okay? All right, and so, I'm bringing together a whole bunch of stuff that we talked about in the past, okay? And the point is that G is written like this. Okay, and these are the components of G. Okay, and so remember that means that G, J, K is obtained by taking G and acting on the basis vectors. In that case, this is d by d qj, d by d qk. All right, so this is how you write down the kinetic energy metric explicitly in coordinates. Okay. All right, so this stuff is parenthetical, so I'm going to erase it. Does everyone have this stuff down here that I'm about to erase? Okay. Okay. Good. So now let's sort of bring this down to earth a tiny bit and look at some examples. Okay, and you'll see that all of this is in practice quite simple. Okay, so we're going to look at two examples, and they're going to be two of the examples that we've been carrying around with us. One is this simple planar rigid body system. Okay, so now I'm going to put the body frame at the center of mass. Okay. All right, and we've done a lot with this example already. So we know that Q is equal to, so it has kind of two flavors. So Q can be either thought of as being S1 cross R2. And so remember that S1 is parameterized by the angle theta there. Okay. Okay, so that's the S1 part, and then the S2 part, of course, is just the XY components of the vector from the spatial origin to the body origin. All right, so that's a kind of a simple representation, but for our purposes here, it's better to think of Q as being the set of R's and little r's in SO3 cross R3, such that, of course, R is equal to cos theta minus sine theta 0, sine theta cos theta 0, 0, 0, 1, and R is x, y, 0. Okay. All right, good. And so, that gives us, okay, so the, okay, so that kind of expresses big R and little r in terms of the coordinates for the system, which are theta, x, and y. Okay. All right, good. So now what I want to do is I want to write down the kinetic energy metric. Okay, so here's how you do that. You use the definition. Okay, so the definition of the kinetic energy metric, and the way that you go about that is you first work with the time-dependent version of the kinetic energy metric. So you suppose that the system is in motion, so everything's depending on t, and then you can freely differentiate things with respect to t to get explicit formulas, and then from those formulas that depend on t, then you back out the formula for the kinetic energy metric G. Okay, so let's see how that goes. So the kinetic energy is simple here, right? So we know all of the components that are involved in this formula because we calculated them already. Okay, so I have 1/2 m r dot squared plus 1/2 IC omega omega. Okay, so everything in that formula we had previously calculated. Okay, so but let me remind you of what those things are. Okay, so R dot, of course, is just X dot Y dot. Okay, so I'm now writing everything in terms of coordinates. All right, so my coordinates are theta, X, and Y. Right, so I'm expressing R dot in terms of the time derivatives of the coordinate functions. Okay, and omega, you'll remember, was R transpose of T, R dot of T, and then omega is a vector in R3, so you have to take this thing and unhat it, right? And so that's just matrix vector multiplication. And again, we did this already, but it's been a while. Okay. All right, so those are all calculations that we can do and we have done. All right, M is M, it's just a number, and I. What we decided was that I had, all right, so okay, so this is a good time to talk about a feature of planar motion, okay? And now what did I say about planar motion and inertia tensors? What I said was that without loss of generality, when a body is undergoing planar motion, you can assume that the axis orthogonal to the plane of motion that the body's moving in, that's a principal axis for the body. Okay, it may not be a principal axis for the body, but I'm saying without loss of generality, you can assume that it is. All right, so here for the first time, we're going to see why you can assume that it is without loss of generality. And so the axis which is orthogonal to the plane of motion of the body is the B3 axis, right? That sticks out of the screen. Okay. And so what I'm going to do is I'm just going to put a number there. Okay. And then I'm going to fill in the rest of it with just arbitrary stuff. Okay. And then the thing we're going to see is that the only thing that matters is that term. Okay. So I'm going to just put, let's say, J11, J12, J13, J12, because it's symmetric. So J12 is equal to J21, J22, J23, J13, J23. Okay, so I'm going to just, those will be completely arbitrary. And the point is, it doesn't matter. All right. Okay. So now we just calculate the kinetic energy. All right. So now this is just a formula. Right. And you just, take some norms, take some inner products. Okay, and you get a formula that comes out of that. Here, and this is what it is. And you'll be unsurprised by what the answer is. Okay. All right. So you would have guessed that anyway. All right, but there is something that comes out of this, and that's, like I said, the fact that even if the B3 axis is not an axis of symmetry, so sorry, a principal axis, the only thing we care about is this number here. So we may as well have assumed that there was zeros there, okay, which would exactly mean that the B3 axis is a principal axis. Okay, so that gives meaning to the statement that I made when talking about planar motions, that for planar motions, you can assume the plane orthogonal to the plane of motion is a principal axis. Okay. All right. Okay, so that's the kinetic energy in the function of t setup. Okay, now what I want to do is I want to think of the kinetic energy not as a function of t, but as a function on the tangent bundle. Okay, and so to do that, I'm going to write it in coordinates, and I'm going to use the coordinates for the tangent bundle. Okay, so Ke of, okay, so it has configuration coordinates, theta, x, y. All right, then it has velocity coordinates, v theta, vx, vy, okay, is simply going to be, so essentially you just replace, x dot with vx, y dot with vy, and theta dot with v theta. Okay, so that's how you can, and this is what you do in any example, is you sort of, in the background, you assume there's some kind of a dummy motion going on, and x and y and theta depend on t. You use this formula to calculate the kinetic energy as a function of time, and then you just do a replacement, right, of the dots with v's. Right, so that gets you the kinetic energy as a function. But now we want the kinetic energy metric. Okay, now how do you get the kinetic energy metric? Well, if you look at that formula, okay, so what I'm saying is I want to get B from F sub B. Okay, and if you think about, and so in this formula, it means you want to get the BJKs when all you know is what the entire function is. And it's pretty clear how you're going to do that. All you're going to do to get BJK is you're going to differentiate this quadratic function first with respect to Vj and then with respect to Vk. And then, out will pop the jkth coordinate, a component of the bilinear mapping B. So that's the technique you use. That's the easiest way to calculate G. To calculate G from Ke, use G jk is d2 Ke with respect to dvj dvk. All right, and again, that's what you always do. Okay, and so we're going to apply that here. And so, a very simple thing happens. There's no cross terms in this kinetic energy metric. It's all just pure squares. All right. So when you differentiate twice, the 2 is going to cancel the 2 there. And then when you differentiate the second time, you're going to get a constant. Okay, so the point is this, is that the matrix for G, okay, so if you take the components and assemble them into a matrix, the matrix is, okay, so the way I've numbered my coordinates is I've numbered my coordinates as theta x, y, right? So the theta part needs to come first. So that's J, M, M. Okay. All right, and the fact that this thing is diagonal, that is just reflected by the fact that in this expression for the kinetic energy, I have pure squares. I don't have like a Vx, Vy term. Okay, so you do get that sometimes, but just not in this example. Okay. All right, or if you want to be grown up about it, which we do, that's how you would write it. Okay, so here I've written the matrix, which is fine. Okay, but you can also write it as a bilinear map, in which case you write it in terms of bases. So we can also write G as J d theta tensor d theta plus M dx tensor dx plus m dy tensor dy. Okay, so either of these ways of expressing g is correct. Okay, what's not correct is to say that G is equal to the matrix. Okay, because G is not a matrix. G is a bilinear map, so G needs to be expressed like that. Okay, it's not a matrix, so this is wrong. Okay, this is okay because you're saying this is the matrix for G, but it's not G. Okay. All right, another example. Okay, so the other example we're going to look at is this stupid robot example. Okay, so I have this two-link robot. Okay, all right. Okay, so we wrote down all of the stuff for this previously. Okay, so and I'm kind of not going to repeat it here because it's just dull and boring. And at some point you realize that there's a device which has been invented, which will do these calculations much more easily than you can on a piece of paper, and that device is called a computer. Okay, and at some point I'm going to sort of demonstrate to you how you kind of write a computer code to keep track of all of this stuff and kind of automate calculating all of these kinds of things, because even for the gyro example that you have on your homework, right? To do some of those calculations is a little bit tedious, and your life is much easier if you do everything on the computer. Okay, so I'm going to stop sort of fully writing everything out for this example because it's kind of disgusting. Okay, but what we do have is we have a theta 1 and a theta 2, and then we have R1, R2, oh, sorry, R1, R2, and R2. Okay, and we have formulas for those. All right, and they involve sines and cosines of theta 1 and theta 2, and they involve the lengths of the little arms of the robot and stuff like that. Okay, and we had also in previous lectures, we had calculated R1 dot, R2 dot, and these ones were the ones where things get a little bit to the point that you don't want to write them down in front of a live audience, not because it's hard to do, but because it's a waste of time. Okay, so these sorry, that's not what we want. We want omega and omega. All right, so these ones were actually easy, right? These ones were just 0, 0, theta 1 dot, and 0, 0, theta 2 dot. Okay, so these were not hard, but just tedious. Okay, and then the problem is that it gets even more tedious, because the kinetic energy is given by this expression. Okay. All right. And we had, again, previously calculated all of this stuff, right? We had calculated the inertia tensors, and the inertia, because this is planar motion, the same kind of observation here will apply. The only term in the inertia tensor we care about is the one on the bottom right. Okay, and so the point is that this part of the expression and this part of the expression are actually pretty clean. So this one just turns out to be 1/2 J1 theta 1 dot squared. And this is 1/2 J2 theta 2 dot squared. Okay. And it's these terms which are unpleasant to write down. And again, it's not like this is difficult. It's just long expressions involving sines and cosines, right? Because you have to take these velocity vectors and then you have to calculate their Euclidean norms. So you take the sum of the squares of the components of those. Okay, and each of the component involves, multiple sines and cosines, and so whoosh, it just blows up. Okay, so best to not show anybody that. Okay, but the point is, there's just an algorithmic calculation to get G. Okay. And it's going to be G will look like this. It's going to look like something times d theta 1 tensor d theta 1 plus something times d theta 2 tensor d theta 2 plus something times d theta 1 tensor d theta 2 plus something times d theta 2 tensor d theta 1. Okay, and the way you get these somethings is exactly like I did in this much simpler example here, right? It's very simple. I write down the kinetic energy, okay, and it's going to involve theta 1 dot and theta 2 dot. And it's going to be a quadratic function of theta 1 dot and theta 2 dot. Okay, then I replace the theta dots with v's. Okay, so it's going to be a quadratic function of v theta 1 and v theta 2. Okay. Then I do this calculation and I get some, either it's going to now be a 2 by 2 matrix because there's only two coordinates, theta 1 and theta 2. And then I can express this matrix like so. All right. So there's two elements of this that I want to emphasize. One is that this is purely algorithmic. Okay, it's just grinding through exactly the same kind of computation with the specific symbols involved with the example that you're working out. Okay, and because it's purely algorithmic, that's good on the one hand because it's purely algorithmic. There's no kind of thinking involved. You just calculate. But the bad part of that is that the calculations can be a little unpleasant, even for a very, very simple example, like just two coupled planar rigid bodies. Okay. All right. But the point is, G is calculated algorithmically from these guys. Okay, so once you write down all the big RAs and the little RAs, okay, and so from your homework problems that can be a job, all right? But once you have that and you've expressed little RAs, big RAs and little RAs in terms of coordinate functions, which you can do, then the rest is just grinding computation. Okay. All right. So now we're going to turn to equations of motion. For mechanical systems. Okay. So finally, after more than half the class is over, we're going to talk about actually writing the equations of motion that describe the motion of a mechanical system. Okay, and we're going to do that in a way which is different from the normal way in which you do things. Okay, so the normal way, normally, one balances forces and torques. Okay, but we're going to do things differently. We're going to obtain the equations of motion by this a methodology known as the Euler-Lagrange equations, which involve crucially the kinetic energy. Okay, and there's this weird set of equations that you write down called the Euler-Lagrange equations, which turn out almost mystically to give you the same kinds of equations as you get from force and torque balance. Okay, so let's first look at the unforced motion of a single rigid body. Okay. So the body is moving around, like so. Okay, so we're going to assume that there's no forces acting on the body. So there's no gravity, no magnetic forces, no potential forces of any kind. It's just freely moving through space. Okay, so the equations of motion, so angular, this is kind of a physical principle, is that and this is one of Newton's laws, when you, at least when you apply it to linear motion, is momentum is conserved. And, you know, Newton sort of expressed it in terms like, you know, a body in motion remains in motion or something like that. Okay, so this is momentum is conserved. So as Newton was certainly thinking about linear motion, there's both linear and angular versions of this. The linear version is Newton, and the angular version is Euler. Okay. Okay, Euler of the mathematical number E. All right. And it turns out that this principle, this actually prescribes fully the motion of a single rigid body with no external forces. Okay, and it does it by we define the two momenta. Okay, so these are the translational momentum. So I'll be literally one more minute. And then the angular momentum, I'm going to call mu. And this is given by, so it's going to be like I omega, but the omega you use is the spatial omega. So that means you actually have to fiddle with your I. I think I have the order right. Okay, so this is a 3 by 3 matrix, and this is a 3 vector. Okay, so this is that right there is matrix vector multiplication. Okay, so this is kind of the inertia tensor, but represented in spatial coordinates because I'm using the spatial angular momentum. And so the physical equations are P dot equals 0 and mu dot equals 0. Okay, so that's how you write down the equations of motion for a single rigid body with no external forces acting on it. Okay, so we'll talk a little bit more about that next time and think a little bit about forces. And then we'll talk about the Euler-Lagrange equations.